Hi, it's Ryan. This is our second example of momentum, and this will work in some POCO as well. So this is a really good example. It's pretty long, and the math may seem a little challenging because I like to substitute in a lot of variables, so bear with me. If you have to pause the video to catch up on some of the algebra, that's okay. But we can get through this, and this is a great example using POCOE and POCOLM. So here we go. A large man named Smoot is running 15 meters per second when he jumps horizontally onto a stationary tire swing with a mass of 25 kilograms. And I've given the rest of the masses at the end of the problem. Upon reaching the maximum height of his swing, Smoot sees a labradoodle that is ambled over and is now sitting underneath the lowest point of his swing. On Smoot's swing by, he picks up the labradoodle, and the Smoot labradoodle tire swing, that's what that is, the Smoot labradoodle tire swing all reach a maximum height, so a second maximum height. Upon reaching the maximum height, Smoot drops the labradoodle. He continues to swing to a third maximum height without the dog. And we're going to have three parts. We're going to have to determine the Smoot tire swing max height, the first max height. Then we're going to determine the Smoot labradoodle tire swing system max height, the second max height. And finally, we'll determine the third max height reached only by Smoot and the tire swing after he drops the doodle. Okay? So I went ahead and drew a few pictures to help sum up what we just read, which again is pretty long-winded, but I broke it into a few pictures, so I'll walk you through them. Sorry again for my art, it's no good. Our first picture, and it shows the first collision. We have Smoot running with his initial velocity and the tire swing just hanging there. I noted that the tire swing has some initial height. Smoot runs, collides with the tire swing, and then the Smoot tire swing system will have a velocity after the collision. And so this picture describes the first collision. Once Smoot collides with the tire swing, which, by the way, this is a perfectly inelastic collision, isn't it? Because they stick together. The Smoot tire swing system swing up to the first max height. At that point, Smoot notices the dog, and so he's on his swing back down. We have a second collision where he picks up the dog. And so this picture is laying out the second collision where Smoot swings down. He'll have some velocity. The tire swing Smoot system will have a velocity before the collision. And then after Smoot grabs the dog, they'll all have a velocity together. Once Smoot grabs the dog, he'll swing up to the second max height with the dog. So that's the second set of pictures, and that's the second thing we'll have to calculate. Finally, Smoot drops the dog, which is a third collision, where we have before, where Smoot is holding the dog, and after, where Smoot has dropped the dog. Something important to note is that when Smoot drops the dog, he's still at the second max height, and they both have a velocity of 0 because they're at the max height, the point where the tire swing stopped moving and is going to start moving back down. So I noted all those things in these pictures. I guess the final picture I could have done would have been Smoot swinging to a third max height. So there you have it. I also put the mass of everything, the mass of the labradoodle, the mass of the tire, and the mass of Smoot, as well as the initial height. So that's kind of our knowns. Okay, and the first part of this problem is asking us to determine this max height. And so really, when we look at this, it should feel an awful lot like a POCO problem, where we have a body starting with a whole bunch of kinetic energy, and all that kinetic energy is getting converted into or transformed, however you want to say it, transformed into potential energy when it stops moving. And so for part A, we're going to start with POCOE. And POCOE will be comparing the total energy here with the total energy here. So notice we're not really starting with before the collision. We're worried about after the collision because it's the Smoot tire swing system that gets up to our first max height. I'm sure we'll need this part, but just not yet. I'm letting the problem guide us. So we know we need max height, and so that we'll use POCOE on the Smoot tire swing system after collision 1. And so what we'll do when we use POCOE anytime is we'll compare the total energy at any point, which I labeled 1 in our first picture, to the total energy at any other point. So at the bottom of our swing, we could have potential and kinetic energy, and at the top, we could have potential and kinetic energy, so I'm going to note that. And I'm also going to say that here, we're going to say that there's 0 potential energy. Even though we do have some initial height, we'll just account for that later when we have to say what H max really is. So we might note that we're saying here PE equals 0. So PE1. So down here, we can now say the potential energy at 1 plus the kinetic energy at 1 will equal the potential energy at 2, the first max height, plus the kinetic energy at 2. These always have the same expressions, mgh1 for potential energy, plus 1/2 mv squared, and this would be v, what we called AST. So it's after the collision for the Smoot tire swing. And that will equal mgh, and we're going to say that's max 1 plus 1/2 mv2 squared. And v2 would be up here, where we could note v2 equals 0. We know the velocity is 0 because it is at the max height. So we'll input those zeros. Height 1 is 0 and v2 is 0. And now we can work through this to get the thing we're looking for, h max 1. So I'm going to divide everything by m, so those turn to 1, and I'm going to divide everything by g, and we'll be left with v after for the Smoot tire swing squared divided by 2g, and that equals h max 1. But this is where we panic because we don't know v after the collision, but we really do. So we'll say we need v after for the Smoot tire. So we're going to use POCOLM because that's a perfectly inelastic collision. So we'll say using POCOLM. POCOLM, we always say that the momentum before the collision is equal to the momentum after the collision. This is the first collision that we're trying to analyze, where Smoot jumps horizontally and onto this tire. And the reason we said that horizontally is so that what that implies is that this velocity direction and this velocity direction will both be horizontal. We won't have to worry about any y direction motion. And because of that, we would say that this is a one-dimensional collision, and so we'll drop vector notation. Vector notation. So we have the momentum of Smoot before plus the momentum of the tire swing before, and that has to equal the momentum of Smoot after plus the momentum of the tire swing after. Well, we know then that the mass of Smoot times the velocity of Smoot before will be the momentum of Smoot, and the same for the tire. Mass of the tire times velocity of the tire before. And we'll write the same thing on the other side, but for different velocities. We might note now, if the bodies stick together, they will have the same velocity. So it looks like this velocity and this velocity, oh, I'm sorry, this velocity and this velocity, these are both VA for this Smoot tire swing system. So I'm going to factor that like variable out. I'm also going to get rid of any zeros we have, which would be the velocity of the tire before. So now we have mass of the Smoot times velocity of Smoot before equals mass of Smoot plus mass of tire times the velocity after for Smoot and the tire, because they're moving at the same rate. That's what we're looking for, so I can solve for it and substitute into my original equation. So we get V after is equal to, and we'll have mass Smoot divided by mass Smoot plus mass tire, all times Vs before, which was given. So we know this value, and so we can take that and substitute it into here. So we can finally get our answer, H max 1 is equal to, and it was this squared. So I'm going to go ahead and put that whole thing in, square it, and divide by the 2 times g, which was in the equation. Now we could substitute all our values in, and if we do that, we would get a numeric answer of 5.98 meters. But H max then will equal H max 1 plus the H sub O that we were given. So our final answer, H max, is equal to 6.73 meters. So that's part A. In part B, we have something very similar happening, don't we? In part B, it's asking for H max 2. And if you then look, don't we have basically the same POCO problem? We have an initial point where we have all kinetic energy, and we have a final point where we have all potential energy. And so we could say, using POCO, and part A, we know that the H max 2 will equal VA2, the velocity, we called it something else, sorry. We called it Smoot Labradoodle tire swing squared over the 2g. So this just came from POCO. We would just do exactly what we did here again, because we would start with all kinetic energy and end with all potential, but it would be for H max 2, and it would be for the tire swing Smoot dog system. So we're kind of ignoring the second collision right now until we need it. But now we need it, because we need V after the collision. So we need to use POCOLM on collision 2. And that's between the Smoot tire and the dog. So we have before the collision, where Smoot and the tire have a velocity and the dog is not moving. And then we have after the collision, where they're all moving together. That's really the same sort of perfectly inelastic collision that we had for collision 1, only now we have 3 bodies instead of 2. So we can use POCOLM. We know the momentum before has to equal the momentum after. The momentum before was the mass of the smoot tire together and their velocity before, plus the mass of the labradoodle times the labradoodle's velocity before, which was 0. And this v before the collision 2 is v after collision 1. So we actually know that. That's this right here. So we know that velocity. What we're looking for is the mass of the system, mass of smoot plus mass of tire plus mass of labradoodle, all times v after for collision 2, which we called smoot labradoodle tire. If you want to pick different names for this instead of all these letters on the bottom, you're welcome to. You don't have to stick to this same the same subscripts that I'm using. Okay, so now we have, we can work through all the algebra, and if we do, we will get VA. VA for the whole system is equal to 9.11 meters per second. And so it's a good little exercise to try to get that value. We can then substitute that into this equation. So we would have H max 2 equal to the 9.11 meters per second, all squared over 2 times 9.81 meters per second squared. And so we'll get H max 2, and this is measured from the lowest point of the swing to be 4.23 meters, and so we'll have to add the 0.75 meters, and so we can finally get the second solution for B, 4.98 meters. And it makes some sense, actually. Imagine if you picked the dog up, it makes sense that you would swing to a lower height. It's going to take more work to move the same different amount of mass up. And finally, for part C, this is where we had collision 3, where he drops the doodle. But something to notice is that he drops the labradoodle, and the before and after momenta are both 0. P before, P after, they're both 0. So there can be no change in momentum or no change in height. Well, that means that the total energy that our smoot tire system have up here would be all potential energy. And so as the smoot tire system make their third swing, they start with PE for the smoot tire system. It gets converted to KE at the bottom, and all of that gets converted back to PE at the top. Since we're ignoring any air resistance like we always do, there are no non-conservative forces acting on the system, and so we can say right away that our H max 3 must equal H max 2 because of POCOE. And so we actually don't have to solve the final part. It's already done. So that's a challenging problem. I left a couple little holes in there for you to do the algebra on your own, but you have the guide, and this is a really good example where we had to use POCOE and POCOLM. Good luck.